Hello everyone. Today we have with us Dr. Brian Diaz, a neuroscientist from Emory University. Anuradha will introduce us to him. Anuradha?
Okay, so here's a brief introduction to Dr. Brian Dias. Brian Dias was born in Mumbai and he grew up in the city. He obtained a BSc degree from St. Xavier's College here in Mumbai, and then he pursued a master's at the Tata Institute of Fundamental Research. He received a PhD in neuroscience at the University of Texas at Austin, and he's currently a postdoctoral fellow at the Emory University in Atlanta after having received a previous postdoctoral opportunity at the HHMI Janelia Farm Research Campus. So we'll proceed with the interview with Dr. Brian Dias. Gokul is going to lead the interview. So Gokul, please proceed.
So, Dr. Diaz, can you tell us a little more about your research interest?
Yeah, so what I'm really interested in is how descendant generations bear imprints of ancestral environments. And if you look at human scenarios and historical events that have gone by, you could take the September 2001 terrorist attacks, and there's evidence to show that babies who were in utero at the time that their mothers directly experienced those attacks in New York bear imprints of that experience in that they have lower cortisol levels at as early an age as 1 year old, and compared to babies whose mothers did not experience these attacks. And so lower cortisol levels we know are predictive of PTSD-like symptoms later in life. And this is the work of Rachel Yehuda and colleagues. And she showed this in Holocaust survivors, and now is also showing this in this population. And you have many historical events like the Holocaust, like the Swedish famines, which suggests that ancestral experiences do profoundly affect descendant generations, and that's really the focus of my research right now.
Okay.
Okay.
So, since you've had an exposure to research both in India and the US, would you tell us how it is done differently here in India as compared to the US?
I really don't think there are too many differences from the perspective of actually doing science. I think, uh, when I was doing science in India, maybe the only real difference was access to articles, which I think may have changed right now. But we didn't have the broad access to electronic articles like you have over here, at least when I was doing science there. The main difference that I think one needs to talk about between doing science in the US versus science in India is just the infrastructure. And this again may have changed. I've been talking to people at TIFR as well as the ISA, so I know change is happening every single day. But at the same time, we used to spend more time at customs trying to make sure our radioactive isotopes didn't thaw out in India, as opposed to over here where you get your reagents in about 3 days. And at TIFR especially, there was a lot of having to push your file from one table to another, whereas here that kind of ordering system, etc., is quite seamless. And so that takes the painful aspects out of the equation, and you can really just focus on your science. And so for me, that's really the main difference. I would say with respect to students, I think Indian students and the science, the way Indian students did their science was on some level of a higher not caliber but degree of efficiency, and I think that is testimony to the Indian education system that we all came from. And so it's very easy for an Indian student to really adapt to the American system because of that particular education.
So, is there a difference in how, researchers think here as compared to those who are there in the US? People who've been brought up in the US, do they think differently when they are doing research? Is their thought process little different from ours?
I
Their
think the
approach.
the thought process is different in that there's a certain amount of I, there's a certain amount of independence and confidence that one sees in students over here. So, for example, students here are willing to take a chance on a particular idea and go to their professor and say, "This is an idea," and the professors, uh, you know, all credit to them, will say, let's try out that idea in most cases. Whereas in India, what I feel is that we're very, very cognizant of the fact that there's a hierarchy, that the professors, etc., might know a lot more than us, and so we're not going to upset that hierarchy by trying to do things independently. And so the research, to my mind, in India was typically driven by the professors, whereas in the US, I would say it's almost 50-50, with research being driven by the professors for sure, but then there's a healthy component that comes from ideas that just come directly from students and postdocs. But I wouldn't say that US students think better than Indian students. That's not what I'm saying. I actually, I wouldn't say that at all. But what I would say is that this confidence that the Americans have does come through in how they approach certain ideas.
All right. Thank you.
So I would inform our audience that Dr. Diaz last year published a paper in Nature Neuroscience where he showed transgender fear conditioning works. It was a very important paper in the sense that it can really change the way we look at behavioral genetics or even evolution. So, can you briefly tell our audience about the work and its significance?
Sure. As I mentioned at the start of this conversation, what we're really interested in is how ancestral experiences affect descendant generations. And when we talk about those ancestral experiences, we talked about the Holocaust, we talked about the terrorist attacks, we talk about stressful environments. And so the idea is to be able to model that in the laboratory. But what a lot of studies have done in exquisite ways is they've taken mice or rats and they've exposed the ancestral, what we would call the F0 generation, to a broad perturbation, a broad stressor. And then they've looked at the descendant generations, the F1 generation or the F2 generations, and looked at what effects this perturbation might have had on descendant generations. What we decided to do was a little different. We decided to capitalize on the specificity that comes with working with the olfactory system. So the olfactory system, or how we smell, is exquisitely organized both structurally as well as functionally in the nervous system. And so what we decided to do was we took the ancestral F0 mice, so adult male mice, and we conditioned them to a particular smell. That is, what we did was every time we exposed these animals to a particular smell, and in this case we used different odors or different smells. One of them is called acetophenone. Every time we exposed the animal to acetophenone, we also administered a mild foot shock to this animal. As a result of which, with this odor shock pairing, the animal now comes to become fearful of acetophenone. We then allowed for some time to pass and then allowed for mating to occur. After which time we looked at the F1 and the F2 generations of this particular F0 ancestor. And what we found strikingly was that with no prior exposure to this acetophenone odor at all, these F1 and F2 generations of mice were more sensitive to acetophenone, and their noses had more neurons that responded to acetophenone at lower concentrations. It was almost as if their nervous systems were now primed to say that acetophenone is important. It's been dangerous to your ancestral generation. You should now be able to detect it in a more efficient way. And then what we were also able to do was we were able to look at the sperm of these ancestral mice, the F0 generation, and we were able to show that there are methylation changes, methylation being an important readout of gene transcription in subsequent generations. And we were able to show that there were methylation changes around a particular receptor that detected acetophenone. So rather than taking a broad environmental perturbation like a stressor or maternal separation for example, what we decided to do was really focus on a particular sensory modality which has a particular receptor which senses a particular odor, and then looked for the what we call the epigenetic signature around that particular receptor.
So you said you found epigenetic, the methylation changes in the male gamete, not in the female gamete.
we didn't we didn't really look at the female gametes. We didn't look at the eggs, and this is a big reason why we looked at sperm versus the egg, is just because you're playing a numbers game. You have many more sperm to work with, and therefore we just focused on the male. We do see that the behavioral sensitivity and neuroanatomical changes also go through the maternal lineage, but at the same time we didn't explicitly test eggs and look at the epigenetic signature around that particular receptor in the egg.
Okay. Do you think the selection of the model organism was very important here? Because I came across a study which did a similar olfactory imprinting study for 40 generations in C. elegans. So that did not receive as much attention, at least in the outside the immediate scientific community. So this was something which was taken up with a lot of interest by the public, the science community. So do you think choice of model organism was very important here? Made the difference?
I don't know whether it's a choice of model organism. Definitely being in a mammalian system is more helpful. I use my PhD was with lizards, and no one really cared about lizards. I mean, I published papers with lizards and didn't get any attention whatsoever. So I definitely think model organisms do matter. But I also think it's a matter of when, and it's just serendipity and timing. I think there's transgenerational inheritance, and research on transgenerational inheritance of traits is really hot right now, and there's a good corpus of work which is being formed and accumulated in the mammalian system, as a result of which I think the press picked it up. I mean, I think the press also picked it up because they had something catchy to say, which was that mice are inheriting the fears of their fathers, which we've never said in the paper, to be fair. But as one realizes, as one goes through this process, getting press is all about it just being sexy, and it's not really a big reflection on the science that's contained in the paper. And so I don't really know what the main reason is. I'm sure maybe mammalian systems have a little bit of an edge, but I think it might also be a matter of uh, coming out at a time where there's all this body of information coming together.
So, um, Dr. Dias, your work has received some criticism, mainly from a certain Gregory Francis. He's called the results too good to be true. So, would you please tell us what is your take on this matter?
So my take on the matter is we welcome the criticism. That's what makes science good, and gets us closer to the truth, which is what science is all about. Uh, I I have no, I obviously don't have the statistical knowledge that Professor Gregory Francis has. I will say that we're in perfect agreement that what really needs to happen is that there needs to be independent replication of the results in a completely independent lab. We're replicating these data, other people in the laboratory are replicating these data over several rounds of experiments, and so we know that the phenomenon is robust, reliable, and reproducible in our lab. But of course, good science needs to be replicated in others, and so I think the proof will be when that happens and when another lab is able to do that, and then I think we can take that conversation between Professor Gregory Francis and ourselves to the next step. But as of now, it's just it's a criticism, and we take all sorts of criticism as being constructive.
Yeah.
So it's been Interesting people. So have people reproduced the work in this time?
Could
As
you
we
repeat
are,
the question, please?
yeah, so uh, uh, it was published last year, so it's been a year. So have people reproduced this work elsewhere now?
Are you talking about in our lab, or are you talking from other labs?
Other labs.
Other labs. So that's a question. We just had the Society for Neuroscience meeting in Washington, D.C., which is 40,000 neuroscientists gather. And I was on the lookout for someone who might have done this experiment and replicated it. But as of now, that doesn't seem to be the case. Uh, but I should say that I worked on these experiments for 3 years. And the fact that there's a transgenerational component means that there's a lot of time that goes by between getting animals and doing your experiments. And so I think a year is too short for there to be any concerted effort. I'm sure there'll be, more results or more replication efforts in the next few years. I think a year is a little too little. But at the same time, I think it does speak a little bit to how science is done these days. Uh, while replication is important, is really crucial, sometimes you also don't want to just do the experiment that someone else has done because it doesn't give you anything uh, novel. And so we hope that that does not happen. We hope that people will do the exact same experiment in the exact same way and not, you know, change parameters or tweak things to get a novel component to that experiment, because a true independent replication of our experiment or any experiment should be doing that experiment the same way. And so we hope that that's happening, but as of now, we don't really know who's doing it. We're just waiting for that replication when it does happen.
So, have you been able to find some mechanistic explanation to this transgenerational phenomena? Were there some early hints or cues which you could share with us?
So that's an active area of research right now, and we're putting our bets where other people have put their bets and have succeeded. So, for example, the lab of Isabel Mansui has shown that small RNAs, microRNAs, are really important and carry crucial information about ancestral experiences, and those in turn affect the descendant generations. Tracy Bale's lab and colleagues at the University of Pennsylvania have also made a very eloquent case for microRNAs and non-coding RNAs being the carriers of this particular information. And so we're putting our bets on microRNAs. We haven't. We just started those kinds of experiments, and data should be forthcoming in the next few months or a year.
Okay. Um,
Yes.
Go ahead.
So another thing I felt, do you feel there is a lack of understanding in the public that the idea that your work is not questioning the fact of evolution, but it is proposing an alternate mechanism in which evolution might operate in addition to Darwinism? So do you think this needs to be addressed and communicated to the public more? Did you find a confusion in the public if you have been communicating it to the public?
We intentionally did not speak about evolution in the paper. And the reason for that is I don't think two generations of mice can speak towards evolutionary timescales that people want to talk about. If you want to talk about evolution and epigenetics, then you have to look at the plant literature where you have 50 and 100 generations of plants that have traits that are epigenetically inherited. And so I personally stay away from all talk about evolution simply because I don't think that a study like mine can shed any light on that purpose or on that perspective. And that's basically my take on on that aspect. I mean, people are free to make, take our studies and do whatever it is and interpret it as however they want to. From my perspective, we just took a very phenomenological data set and then tried to ascribe a mechanism to it. But to say that there's an evolutionary implication here, I don't think I would discount that pretty vehemently.
But I mean, to study such a mechanism in which evolution might operate, I think we really need to look at in higher organisms like mice. I mean, the soma and gamete interaction. I mean, acquired characters. We need
Right,
to.
but I guess if we're going down that route, I mean to my mind, evolution operates or evolution also needs to fix certain traits over extended periods of time. We're talking about epigenetic marks in the genome, which we know are very dynamic. And so the fact that marks are dynamic would probably mean that they don't hang around for too long, as a result of which they might not get fixed. Now, if there's a secondary mechanism by which a trait gets fixed after the epigenetic mark is stripped, one doesn't really know. But at the same time, prima facie, I would say that the dynamic nature of an epigenetic mark by definition would mean that you can't really speak about evolution in that perspective. And so that's why I don't really think about it from an evolutionary perspective until I can say that that mark which we saw then affects transcription of that gene, and that transcription is affected even in the absence of that mark for many, many generations to come. Hence my reluctance to go down that particular route.
Um, okay, so in conclusion, we'd like to ask one more question. Do you have any plans of coming back to India and doing some good research in neurobiology here?
Yeah, so that's a good question. Every time I come to India, I do try and give a talk, at TIFR, or I'd really love to go to the ISAs and give a talk. I mean, there has been talk about, uh, I would like to think about the ISAs in the future. It's just that at this point, with the kind of science that I'm doing and the kinds of mice that I need and the ecosystem, I think. The States is where I'm going to start off my career, but at the same time, I have a very strong urge to come back and contribute to the system that, in essence, has made me who I am. I make no bones about that. We started off this conversation, talking about the differences between the US and India, but I am the scientist I am in large part because of the Indian education and the Indian scientific experience that I had. I do want to give back to that. I'm just not so sure that I'm going to go back right now. I think in the future I will, and there are very, very many ways to contribute to uh, the benefit of Indian science, even from afar, and that's what I'm going to focus on at this point.
Thank you, Dr. Dias. That was a wonderful insight into your work and what you're doing currently.
Thank you very much for your interest again.
Thank you so much.
You're welcome.